Hello everyone. I would like to welcome you all to the APRU Sustainable Waste Management Global Lecture Series. I'm Pavani Disanayaka, a PhD scholar from Korea University, and I'm going to host this event together with Professor Oak. Before starting today's event, I would like to invite Ms. Kumudini Palansurya to provide some technical instructions for the webinar logistics for the attendees. Ms. Kumudini, over to you.
Hello, everyone. Thank you for being with us for the fifth session of Global Lecture Series. As Pavani mentioned, I'm going to collaborate with you with the webinar logistics today. I would like to give you some recommendations to be considered during this event. This is the webinar mode, so you can listen and see the panelists, and also you can interact with them through the chat function during the webinar. We have enabled 2 chats, so you can ask questions to our speaker anytime through the Q&A chat and also through the general chat. If you are interested in talking and asking questions directly, please raise your virtual hand so that I will allow you to talk with the speaker directly. As it is an international event, I would recommend you to use your English name all the time. Other than that, if you have any problem or any issue during the event, please feel free to send me a message via chat function so I can help you. Thank you. So I hope you will enjoy the event.
Thank you, Kumudini. APRU Sustainable Global Lecture Series is organized by the APRU Sustainable Waste Management Program, where Professor Young-Sik Ok at Korea University serves as the director of the program. The program is co-directed by Professor William Mitch at Stanford University and Professor David Waddell at Nanyang Technological University. Today's lecture will be delivered by Professor Johannes Wehemann from Cornell University in USA. The title of the lecture is Waste Management Using Biochar in Mitigating Climate Change and Securing Water Quality. At the end of this presentation, there will be a Q&A session. I encourage all the attendees to participate in the event actively and come up with your questions for the discussion. Now I would like to invite Professor Young-Sik Ok to give the welcome address.
Okay, thank you, Pavani. Hello, everyone. I'm Young-Sik Ok, who is the director of APRU Sustainable Waste Management Program and the chair of this session. So APRU has a membership of the president from 57 leading universities from around the Pacific Rim. This includes more than 2 million students and over 200,000 academic staff. So APRU Sustainable Waste Management Global Lecture Series is designed to provide a sound foundation in basic principles and unifying research across ecology to conservation and environmental health to waste management, while paying more attention to environmental, social, and governance and global sustainability. Particularly, some related topic will be discussed through APRU Sustainable Waste Management Global Lecture Series, focusing on each pillar in ESG. The key topic of our lecture series include conservation, ecology, environmental chemistry, environmental health, resource management, sustainable waste management, and global sustainability, as well as life cycle assessment. So as you know, we have consistently tried to carry out a variety of programs designed to accelerate academic activity and international cooperation. So APRU Sustainable Waste Management Global Lecture Series is actually a part of regular range of events offered by our program, and is designed to offer the audience an inside view of cutting-edge research topic. And I believe the participant will be able to learn from and interact with world-renowned scientists around the world through this lecture series. And I'm really honored to host Professor Johannes Weheman's talk today. And I also hope that this event will become a valuable opportunity to extend and share friendship among those who participate in this webinar. Thank you very much. Thank you.
Thank you very much, Professor Ok. Now we will move to the 5th lecture of Global Lecture Series. I would like to invite Professor Daniel Sang from the Hong Kong Polytechnic University in Hong Kong, China, to introduce today's speaker. Over to you, Professor Sang. Professor Sang, can you please unmute?
Thank you. Thank you, Pavani. It's my great honor for me to introduce the speaker, who is Professor Johannes Lemon from Cornell University, USA. Before the lecture, I would like to give a brief introduction about Professor Lemon. Johannes Lemon, Liberty High Bailey Professor of Soil Biogeochemistry and Soil Fertility Management at Cornell University. He received his graduate degrees in soil science at the University of Bayreuth, Germany. During the past 20 years, he has focused on nanoscale investigations of soil organic matter, the biogeochemistry of pyrogenic carbon and sequestration in soil, sustainable land management practices in tropical agriculture, and biochar bioenergy systems. And Professor Lemon is a member of the steering group of the International Soil Carbon Network, has testified in the US Congress, and briefed the President's Council of Advisors. Professor Lemon has over more than 200 journal publications. He has been named as a highly cited researcher by Thomas Reuters since 2014. Hans Fischer Senior Fellow at the TU Munich and Humboldt Fellow, and a member of the German National Academy of Science. And he co-founded the International Biochar Initiative in 2007 and has served as the chair of his board of directors with interruption from 2007 to 2016. So Professor Lemon, over to you, please.
Thank you very much, Dr. Sang and Dr. Ok and the whole team for hosting this intriguing event. I'm really pleased for joining this illustrious series of speakers and share some thoughts on biochar systems and what biochar systems might mean for mitigating climate change and securing water quality. The initial motivation over the last couple of decades to explore biochar, in my view, stem from the examination of these terra preta soils in the central Amazon. Archaeologists, anthropologists, and geographers in the 90s accelerated research on investigating these pockets of soils that are scattered all around the Amazon that are very fertile, bear large carbon contents that was derived from Amerindian populations several thousand years before present. And it turned out that most of the carbon in these soils that is persistent is several thousand years old. So that provided an incentive to think about biochar type carbon as a soil amendment. What is biochar? Biochar is a thermochemically converted biomass. It is made by heating biomass under the exclusion of oxygen that leads to the condensation of carbon structures to produce amorphous carbon and tropostratic carbon, release of hydrogen and oxygen. And that also means that this material becomes increasingly persistent. Biochar is actually not a new product. There are very interesting agricultural texts that reach very long in the past. Several hundred years ago, a lot of agricultural textbooks from the mid-1800s discussed charcoal as a type of manure. And there were even products that were advertised, as you see here, charcoal products that are added to soil and make the soil better and even have the ball bounce a lot better. And maybe the European Championships in soccer should try this out this week to make the turf better. Biochar is also not a unique substance to soil management, but is a a part of the Earth system cycles and part of carbon in soils on a global scale. We don't have a good grasp at the moment how much biochar type carbon ore in the Earth system sciences, it's usually called pyrogenic carbon, is there on a global scale. But from this map, you can appreciate that it is ubiquitously present in most soils across the globe. So what biochar management actually is a management of existing carbon in soil. Biochar is, of course, a word for a material, this thermochemically converted biomass. But I like to look at it really as a system that appreciates that we have to look at what we make biochar from, biomass at the front end, whether that is waste materials, even excreta, manures, or purposefully planted bioenergy crops or residues from agricultural production or food processing. That is then converted using heat treatment to produce gaseous products. Those can be condensed into liquids or converted into liquids biologically and physically, or gas products that either generate energy or other co-products up to cosmetics. On the other hand, the solid product that we now call biochar may be returned to soil as a soil amendment, and you'll have to forgive me that as a soil scientist, I will focus today on its soil application. But of course, there are many novel applications that are in material science, building material, and other bioproducts, which I will not discuss to any degree today. When considering the application to soil, there are really three major entry points in terms of its climate mitigation approaches in biochar system science. One is that while we're making biochar, we are producing or can produce an energy product. Of course, the bioenergy industry might think exactly the opposite, that we produce in the first instance a bioenergy product, and we may produce some biochar, or we may not. We may also use that for energy generation. But of course, this energy product will offset fossil fuels, which is one important part of the climate mitigation benefits of a biochar system. When we add biochar to soil, which I focus on in this talk, then we generate a carbon sink. The biochar itself constitutes a carbon sink. But also, we are reducing other emissions such as CH4 and N2O from that charring of the biomass, especially if that material that we would otherwise have not pyrolyzed ends up in a situation where it generates methane or nitrous oxide. The third entry point is then the emissions from the soil or the ecosystem that it was added to. And that generates also carbon dioxide removal and emission reductions. It may reduce greenhouse gas emissions from soil, carbon dioxide through negative priming, N2O, and CH4. But it also might increase crop productivity, or in general plant productivity, through increased photosynthesis. So all these three entry points together have to be considered in a life cycle assessment for its effects on total systems, life cycle emission reductions, and carbon dioxide removal. So I'll walk you through a few chapters, 4 chapters in my talk, and start with what I would consider the linchpin of biochar systems and its mitigation effects, and that is the persistence of the material that we produce, the biochar itself. Unpyrolyzed organic matter is biomass, plants, woody biomass, straw, crop residues that through heat treatment generate increasingly fused aromatic ring structures that have cluster sizes from just a handful of aromatic clusters to several dozen aromatic clusters at a few hundred degrees Celsius. And concomitant with those generation of fused aromatic ring structures, the material persists longer, about an order to 2 orders of magnitudes longer than the original material would have persisted and under the same environmental conditions. Of course, the environmental conditions might vary dramatically, but so this statement is really meant to be a relative statement between charring and not charring. We increasingly recognize that this property of fused aromatic ring structures is key for its persistence and longevity in the environment, which relates this condensation and fused aromatic ring structure relates to the hydrogen to carbon ratio, whereby less hydrogen is indicative of a greater proportion of fused aromatic ring structures. The global data set at present shows that there's quite a range of different decompositions in soils depending on chiefly the properties of this material. And here you see the relationship between this H to C ORC ratio as an indicator of molecular condensation to the mean residence time at a certain temperature, here calculated for 10 degrees mean annual temperature. This also means that with higher temperature, where we generate more fused aromatic ring structure, we typically have a greater persistence in the environment. Here expressed as the fraction of biochar carbon that remains after 100 years. You see here that material in this global data set that have been pyrolyzed between 350 and 450 degrees, the average persistence is about 65% or a factor of 0.65, whereas high temperature biochar in the realm of biochar between 600 and 700 degrees shows a fraction that remains after 100 years of close to 90%. These kind of data can then be used for a practice-based prediction of persistence in the environment, and that has found entry into an appendix of the latest national greenhouse gas accounting guidelines, and in a modified form are proposed for the forthcoming guidelines for the USDA national greenhouse gas accounting in the US. But obviously, the persistence of biochar is, while it is an important part of the system's emission reductions, it is not a sufficient part or sufficient for considering the emissions of the entire system. So we really need to look at total life cycle emission reductions from what is happening at the front end with photosynthesis, what is happening during pyrolysis, and then all these indirect effects that I told you about in soil, as well as any emissions from transportation or especially land use change, and calculate the net balance of that. All these emissions need to be considered for these this accounting, but some of these can be to facilitate methods at this juncture can be ignored if that is a conservative assumption. So some of these emission reductions might be small or might be what might facilitate a conservative assumption might facilitate accounting in the near future. In the medium-term future, we would hope that modeling and data management tools are available, that these can be fully accounted and recognized. This is one example of a full life cycle assessment looking at the comparisons between different feedstocks, and that is really an important part of the emissions. What would have happened with the feedstock and the biomass if biochar and pyrolysis would not have been implemented? Whether we have a crop residue that is accumulating but need to be collected, whether we have yard waste, for instance, as a stand-in for a feedstock that is accumulating and is already collected, doesn't need to be collected, and the other extreme being a feedstock that is actually need to be grown and might trigger indirect land use change, here shown in yellow. And you see that the net emission reductions here shown behind this word net are dramatically different depending on the feedstock and the situation. But you also see, so we need to include these moving parts in a full accounting. You also see that on the reduction side, the emission reduction side, that this blue part of the stacked bar chart is an important portion, and that is the persistent biochar. So you see and appreciate that a lot of the emission reductions, typically half of the emission reductions of a biochar system, is delivered through the biochar carbon itself. This particular accounting does not consider any soil effects in terms of photosynthetic increase of fixation of CO2, and under that assumption, the sequestration and emission reductions through biochar addition to soil is more or less equivalent to the energy emission reduction if the biochar would have been used for fossil fuel offset. So that shows you that there is a clear trade-off between the emission reductions and carbon sequestration. And this is something very important to recognize, also to benchmark against alternative approaches that we might consider. Here just shown two other approaches that we might consider in the landscape. One is restoring wetlands, where a lot of carbon is stored in the wetland through restoration, or a assembly of cropland management strategies, such as different intercropping and agroforestry, as well as tillage reduction strategies. And here you see shown the carbon dioxide removals. So this is the increase in soil carbon sequestration, but shown as in carbon units, versus the system greenhouse gas emission reductions that, of course, not only include the sequestration of carbon in soil, but also in the case of biochar, the emission reductions through fossil fuel offsets if bioenergy is produced. But it also means that there are offsets in terms of N2O emissions and potential CH4 emissions from restoring wetlands. The one-to-one regression here indicates that there's as much carbon dioxide or emissions equivalents avoided as there is carbon sequestered and removed from the atmosphere. For biochar, it seems on a global scale that there's slightly more greenhouse gas emission reductions than there are carbon dioxide removal in the same unit, whereas some of the carbon dioxide removal through soil carbon storage in restored wetlands are offset by emissions such as CH4 and N2O. So this is an important way of looking at systems options for biochar in general. And if you see here, this is the same data. This is where the global average biochar potential, technical potential lies, as far as we know. So if we think about increasing emission reductions at the same carbon dioxide removal intensity, then we need to think about how we can reduce CH4 and N2O emissions or increase energy generation at the cost of lower sequestration and carbon dioxide removal. We might also consider optimizing biochar systems in terms of greater greenhouse gas emission reductions and greater carbon dioxide removal, and that may be delivered through prioritizing plant growth increases or lower, more negative priming. And you can see that, of course, when we utilize unsustainably harvested biomass, that we might increase other greenhouse gases, even though we might actually reduce atmospheric CO2 and increase CDR. We might actually increase greenhouse gas emissions. So such a decision system might help in optimizing and also identifying trade-offs that one might need to be aware of. I mentioned that a key factor in biochar systems is the effect on plant growth. That's one of the key mechanisms whereby adding biochar to soil is a better approach than offsetting fossil fuel emissions. So we would want to look at the relationship of this kind of carbon accrual with different approaches, whether it is biochar or cropland management or set-asides and restored wetlands against food production changes. So far, now we think that biochar additions to soil in most cases will increase crop yields, and I'll show you some data on that. And that up to a certain degree, adding more biochar to soil will also increase crop yield. But we don't know really what that relationship looks like, indicated by these diamonds here. Is there a quick saturation of the response? And what is the ceiling of this response? So those values here are indications of meta-analysis, but it's not clear what the global ceiling is. In restored wetlands, you might assume that restoring wetlands might increase crop yields, but on the long term and with a full restoration, of course, you are replacing a crop production system with a natural wetland, and then you completely reduce crop production to zero. And the question is now, what's the relationship here? Can we keep crop growth high or even increase it a little bit when we increase soil carbon contents by restoring wetlands, and what this relationship is? But definitely it's a downward relationship. This is also there is a trade-off in there, but it's also an incentive for adoption, and that is something that has been recognized for quite a while. Global meta-analysis show, and you can look at calculating these in many different ways. Somewhere between 11 and 28% of the global mean increase. But those are, of course, include all treatments that you might think of in an experiment, also those that were possibly never meant to be adopted anywhere. What you also see when you look at the scatter of the different crop yield responses, whether you add manure biochars, non-woody biochars, or woody biochars, to a whole host of different crop types under greenhouse or field conditions, you get vastly different responses. Some of that is, of course, scatter in the data, is uncertainty and variability, but some of it is also data that we would like to know more about. How far really can we increase crop yields with some of these approaches under some conditions that we would then select for. In this assessment that looked at pairing always biochar additions with and without inorganic fertilizer, we can see something interesting. First of all, just adding biochar in most cases, and the global average shows it's not significant, although it's a small increase, it is not significant, does not generate large increases under most circumstances. But adding inorganic fertilizer plus biochar, the increase compared to inorganic fertilizer additions is somewhere on the same order of magnitude, 26% versus 22% in this study. Plotting the fertilizer effect against the biochar effect. So what is at the same location, what is the effect of adding fertilizer versus adding biochar on top of fertilizer, gives you hardly a relationship at all. So that means the biochar additions, or this would be my interpretation, that biochar additions really don't address the same crop yield constraints that the nutrient additions at this site address. So that is kind of interesting and gives us some pause to think about. Now, there might be some situation where biochar additions really mitigate an issue that just with fertilizer additions we cannot address. And vice versa. In some situation, biochar additions might do very little. And fertilizer additions are really much more effective. In that sense, it is a really useful complementary management strategy to inorganic fertilizers. In this next section, I would like to highlight the energy component of this that I mentioned earlier. Pyrolysis or other thermochemical conversion strategies can generate a whole host of energy carriers through nuances of different technologies, and all that this that I might want to indicate with this chart is that there are also a lot of connections that we might explore. So that I might not be one approach to generating energy or a bioproduct, but many different ones, and they might be also usefully combined with each other. As I said earlier, there is an obvious trade-off between generating energy and generating biochar. Here, an energy tracking analysis for the energy units here in gigajoule per ton of dry ash-free biomass, for 20 gigajoules per ton of biomass feedstock in, we are generating about a little less than half the energy contained in the feedstock as energy products, and about half of the energy remains in the biochar. Obviously, those kind of energy sequestration might be of detriment if we want to maximize energy generation and fossil fuel offsets, and this has to be considered in these kinds of assessments. Looking at several different approaches for energy generation, looking at the biochar yield on the x-axis in tons of carbon per tons of dry matter of feedstock, and the fuel yield on the y-axis. will immediately appreciate this negative relation, this trade-off between one or the other. You also see that the lines are not all parallel, and that some of the lines overlap, so that there is a lot of optimization possible. And these are a whole host of different conversion technologies and different pyrolysis and other thermochemical conversion technologies. So looking under the hood of these different technologies and their energy products is warranted. But none of this should make us blind that there is energy in the sequestered material. If we only generate energy in a bioenergy system, we're emitting all the carbon from biomass. It's at best carbon neutral, and we're generating 100% of the energy that is contained in biomass as for fossil fuel offsets. In a biochar system, we're only generating, say, for a slow pyrolysis system, 50% or a little less energy, and sequestering 50% or a little less of the energy in the soil. This is only tilting towards an advantage for a biochar system in terms of emission reductions if there are other emission reductions, such as greater crop growth or other greenhouse gas emission reductions from soil or wherever else you add it, if it's not soil. A carbon capture and storage system, or BECS, would always win on amount of energy produced and emissions sequestered. Now, obviously, you can also combine these, that these emissions from biochar systems can be sequestered similar to as a CCS system. And one might ask the question whether organic carbon in soil or in other building materials or in other bioproducts create greater societal value than CO2 injected into the earth. So those are questions to be asked. I would like to, in my last chapter today, I would like to talk a bit more about water quality, because I think it is very important, obviously a very important resource, but it also intersects very importantly with climate mitigation, and is a complementary approach to waste recycling that goes beyond thermochemical conversion. Especially manures and human excreta as the largest untapped source of nutrients have been utilized in history for a long period of time. So this is in the English language under night soil is a very common approach to nutrient management in agriculture that reaches back hundreds to thousands of years. But also using recycled and especially biochar products as fertilizers and as tradable commodities has been observed in industry for a long period of time, and is something that we might want to consider again. Historically, we have seen this detachment of carbon, energy, and nutrient cycles in our society from pre-industrial agriculture throughout history, the last few hundred years. And the question is whether biochar technology and pyrolysis might we might be able to reconnect some of these nutrient, energy, and carbon cycles. A local story from around here, but probably that is a ubiquitous issue. I'm from Germany originally, and I know it was when I was growing up, it was a big issue, harmful algal bloom, that lakes were closed. This was not an issue when I arrived in the US. Around here, we have beautiful lakes. But now, the last 3 years, these lakes have been closed for a good part of the summer because of toxic algal bloom that comes from, in this case, animal manure runoff into the lakes. And since these are really important for the local economy and tourism, this is a high priority political item. But of course, the Gulf of Mexico and other estuaries around the world experience similar related issues with no differences between salt and sweet water, nitrogen and phosphorus issues. Just as a teaser, it is very telling that there is as much phosphorus, and this is tons of phosphorus in dairy manure in New York State, as there is phosphorus applied to crops in New York State. So the amounts of in just this one feedstock of dairy manure, the amounts of nutrients that are going around are not allocated appropriately. Obviously, a lot of it ends up in our beautiful lakes, and applications of commercial fertilizer tells you already that this is that there are some opportunities. If we look at this on a global scale, we actually realize that this is more common than just a local story from upstate New York. That actually a lot of nutrients, nitrogen, phosphorus, and potassium, and the top chart here is nitrogen, the middle one is phosphorus, and the bottom is potassium. We are flushing down the toilets, or we are not efficiently utilizing in terms of animal manures globally. And the color chart here is, if it's red, then we are actually have more nutrients, in this case, in the top case, nitrogen, than we apply with mineral fertilizer in that same country. And you see some countries stand out here in more redder colors. And it's actually more than half the countries, about a third of the countries have more nitrogen and phosphorus and potassium in even human excreta that are not used at all. And this is, of course, a huge problem for the environment, but also a huge opportunity for the circular economy and climate change mitigation. In principle, just as a thinking model to move us from, in this case, animal husbandry, a conventional manure management that we add the manure to the fields, and some of that will end up in our water resources, causing harmful algal bloom. We might employ three different approaches here. One is to decontaminate and reduce leachability through pyrolysis and biochar. One is to absorb phosphorus and nitrogen with biochars added to soil. And the third one, I think that is the most interesting one, is to make a tradable commodity out of high nutrient containing waste feedstocks that then can enter the global fertilizer market and be applied where it's needed and not disposed of nearby. In terms of the example of dairy manure, when we screw press and pyrolyze dairy manure, we reduce mass by 96%. We reduce leachability of phosphorus by 90%, and we increase plant availability of phosphorus by 96%. And that has a commercial value here, just some preliminary data for New York State. And so this should be considered as a viable alternative. Nitrogen is a specific case in this context, because as those of you who are more familiar with biochar know that nitrogen is as with carbon, when we pyrolyze a manure or high nitrogen containing feedstock, we are volatilizing about half of the nitrogen, and much of the other half that is contained in biochar is not available to plants over any meaningful timescales. But we might be able to design biochars that they are capturing nitrogen, either in solution or, as shown here, through gaseous reactions of ammonia and H3 gas with oxidized surfaces. And that might be relevant for managing animal agriculture, as well as generating a viable fertilizer that might enter industrial fertilizer trading schemes. We've shown that with suitable modification, especially oxidation of the surfaces of biochars, we can generate biochars that are very efficiently absorbing ammonia and generate a biochar product that has more than 10% nitrogen in it, which is more than any other biological material that we can generate through manure or plant products. If we're looking at the value of these kind of nutrient-rich products, and in this case we're just looking at phosphorus and just the conversion of excreta, in this case poultry, but you might just consider that as a thinking model for other nutrient-rich materials. We can look at possibilities of different conversion technologies, whether it's a thermochemical conversion or anaerobic digestions or gas conversions, and look at the effects on life cycle emission reductions, as well as the effects on other environmental services, including and chiefly water quality. Just looking at benchmarking the effects on human health, on ecosystem quality, on climate change and resource depletion with a direct land application of poultry litter, so modified poultry litter application, we see that at least for these conventional life cycle assessments that give different eco points for different value streams, we see that all these conversions improve human health and ecosystem quality, especially water quality. All of them mitigate climate change, and to the greatest extent here, the pyrolysis strategies, whether it's slow pyrolysis or fast pyrolysis. Only with resource depletion, the fossil fuel offsets are rewarded in these kind of calculation exercises to a large extent. So those approaches that generate more energy also fare better in these kind of analysis. My last two slides here show something that I think is in this context really important is these the spatial assessments, and this hasn't been done to a large extent for global scale or even regional scale analysis of resources. But just as a thinking model here for the state of Georgia in the southeastern United States, looking at here on the right side, the blue map shows where poultry litter is produced. So this is a big state in the United States that has a lot of poultry production. Where it's bluer, the map, there's more poultry production. That means also more litter production in these counties here. The different polygons here indicate counties. On the other hand, if we look at the distribution of different soils and their need for phosphorus additions to grow crops that we know are grown in these areas, we see that these two maps, right and left, don't overlap to a great extent. Wherever we have the largest amounts of poultry litter production, we don't have the largest amounts of phosphorus and therefore biochar needs. And vice versa, down here, there's a lot of need for biochar and phosphorus, and we have very little poultry production. So how do we get the phosphorus from up here to down here where it's actually needed? And that is an optimization problem that touches not only on phosphorus needs, transportation distances, location or conversion, but of course also the effects on greenhouse gas emissions, carbon sequestration, and feasibility in terms of economic revenues. So we can think about this as looking at the trade-offs between emission reductions and profitability. We can look at it in terms of where is the net carbon dioxide sequestration the greatest versus emission reductions. And in this particular exercise, through optimization modeling, we came up with this map that would locate conversions or pyrolysis units in these different locations, as well as centralized upgrading facilities for liquid fuels, and then transportation of biochar and phosphorus to crops in different counties. There are these orange arrows. And then you can identify an optimization where you still maximize emission reductions with profitability and carbon sequestration benefits. So sometimes take-home messages of these kind of discussions that there are some trade-offs, but also synergies between food production and CDR possible for biochar. I see a distinct synergy there. Actually, it is. We might even say it's a necessary synergy because without greater crop production, in most cases, we will also not see a greater CDR of a biochar system or greater emission reductions of a biochar system compared to offset of fossil fuel. But local optimization is possible and needed. You see that we have seen that great spread between fertilizer responses versus biochar responses. That is not just important for climate change mitigation, but also as a key incentive because a farmer's business is growing crops. And if we can support that, that will be a huge incentive for land-based CDR. In biochar systems, it seems that on a global scale, it looks, with the data that we have, it looks as if CDR is greater than expected from life cycle emissions alone, but there are a lot of moving parts. There are N2O emissions, etc. But that applies not just for biochar systems, but also for any other systems. There is a trade-off between energy and biochar that I've shown, and it comes down to also a geopolitical and societal prioritization. What is more important to us, healthy soils or more fossil fuel emissions offsets? And I see a clear potential for water quality improvement with suitable industry development that makes fertilizer companies from mining, changes the industry from mining companies into recycling companies. But the technical potential and the economics are largely unquantified for that. And with that, I'll thank you very much for your attention. I want to highlight that, biochar, I looked at soils, but it's not just soils. And I know that there are a lot of activities that are not soil related, but you'll forgive me if I focused on soils for today. Thank you very much, and I look forward to the conversation.
Thank you, Professor Johannes, for a very interesting and informative talk. And I fully enjoy your talk again. So I believe that the audience also fully enjoyed the talk as well. So now the floor is open for the audience, for any of you who may have any questions in mind. So please grab the chance to pick Professor Johannes' mind and our opinion on your questions. So please feel free to maybe unmute yourself or type your questions in the chat box, please.
Hello, Professor Nandi Bolan. Thank you very much for joining this meeting as a panelist during your busy schedule. I understand you're currently attending a conference, so I guess you have run out of time. So if you have any question or comment, can you share with us? Thank you.
Good morning. Thank you, Professor Young-sik, for the invitation. Professor Johan Lyman, thanks for your colorful and comprehensive presentations. I understand you covered 4 chapters, starting from persistence of biochar in relation to long-term carbon storage, covering the full life cycle analysis in relation to emission reduction, linking to bioenergy production. Chapter 2, carbon dioxide removal and food production, with a very fantastic global meta-analysis on crop yield. It's pretty interesting to note the value of the combination of fertilizers with biochar. Pretty interesting observation. And then you went on chapter 3, which is energy generation. That's in relation to mass and energy tracking analysis. Pretty in-depth analysis. And chapter 4 is the final chapter, water quality and fertilizers in relation to what I call smart recoupling of nutrient cycling, thereby reducing nutrient losses to the environment. In that, you have covered the uncoupling of biochar, that is phosphorus demand, and poultry litter production with an optimization to avoid that uncoupling. So it's a great presentation. I'm looking forward to some of the questions. If there is no question, I may probably start with the questions. So first I will wait for the questions from the audience before the panelists start asking questions. Thank you, Professor Johan Lyman.
Thank you very much,
Thank you,
Ms. Bolan, for your kind introduction and comment. If you see the chat menu, we got several questions from the audience actually. So just let me quickly ask a question on behalf of one of the participants. Is asking, dear Professor Lehman, could you kindly provide some information about large scale and mega project on CO2 capturing with the biochar? What are the challenges facing when use biochar in real world application for CO2 capture? That was one question. And there was another similar question. How can we achieve carbon neutrality by different country by using biochar? Those are pretty big questions. So.
Yeah, no, thank you very much. Thank you, Nandi Young-sik. That's good questions. Those are more industry-related questions, but my I'm sure imperfect reading is that companies and municipalities are still exploring the value proposition of biochar and biochar systems, and that the engineering solutions to scale this to a meaningful scale it's a work in progress, and that there are companies that are, and one of them we visited together in South Korea not too long ago, and in many other countries there are companies who are exploring that, whether it's on individual enterprise such as dairy production systems, municipalities, or dedicated pyrolysis facilities that are selling a product that goes back into the into a certain commodity stream, whether it's whether it is soil enhancers or fertilizers. So those, as far as I can see, this is happening. If you had asked me in 2011, 2012, there were really no commercial products. And about 4 or 5 years ago, there were commercial products, but they were really only starting to sell. And now my assessment is that there are viable industry that are starting to expand and starting to reach scale. But of course, compared to the fertilizer industry that produces NPK fertilizers, or the compost industry, or the municipal waste management industry, it's very, very small still. And that is maybe also good because there are a lot of engineering and product kinks to be addressed and to be optimized, because an approach such as this one is probably best situated when it unfolds its full suite of sustainability benefits that includes, yes, climate change mitigation, but as I pointed out, without, in the case of a soil amendment, without a tangible and financial benefit to the farmer. This is both from a climate change mitigation angle as well as from an economic and an equity angle, really not just justifiable.
Thank you, Professor Johannes. Since we are speaking of the commercial sector and the financial viability, actually we have another question from Professor Hailong Wen asking about what is the potential for biochar to be applied to carbon trading. Yeah,
that's a good question, and I know that's a little bit of a hot item, not only in the biochar discussion, but in general, but also in the biochar industry. And science, because there's some interest in industry to tap into carbon trading mechanisms, and I do find it very intriguing to think about a nature-based solution, or comparing it with, let's say, reducing tillage or agroforestry or crop residue conservation tillage, conservation agriculture, to think about a technology such as biochar where the monitoring might occur at point of conversion, and where with relatively little further monitoring, such as proof of application of the biochar and sustainable feedstock production, one may enter a viable carbon trading scheme without the need of elaborate continuous monitoring of the sequestered carbon at the back end, which we have to do in most cases, or now location-specific process modeling and practice modeling for other sequestration techniques. It's good to see that there are some trading schemes that are being developed, whether it's through VCS or other mechanisms. So private companies that are offering those schemes. So I hope that that's done in a way, and this is where science, I think, is really tasked in examining the different approaches very carefully to see that they are scientifically defensible. But there's definitely a moment in time where there's a lot of movement in that area for biochar and otherwise.
Thank you. And I also see that actually there's a lot of questions on the chat box, so maybe we may miss some of them, but maybe I see some questions. Maybe we can start with them. So the audience have some interest about whether your perspective on the conversion of food waste to biochar, there's one question from one audience, and the other audience asks about there's a lot of like chemical modifications or other modification methods for the biochar, and what's your view on those chemically modified biochar in terms of the soil applications from your perspective as a soil scientist? So please.
Yeah, so that's a very interesting area. I think that's a good to highlight that. Well, first of all, we know that there are many different soil productivity constraints that a farmer or a land user might want to address, from soil physical constraints, tilth, and water relations, whether it's infiltration or water holding capacity, to nutrient retention, pest infestation, you name it. And of course, as one might expect, and every farmer and land user knows, there's not one switch that I should be flipping to make all this happen. No, one wouldn't expect that one of anything would address all these aspects for all sites of the world. So obviously, if we have identified a soil constraint, then we would want to design a amendment and see whether a certain biochar type, a modified biochar, would address that constraint. I do see the need for tailoring biochar properties exactly to that, and I think modification of biochar, post-production modification is a large part of that. The combination of nutrients or microorganisms with organic matter, and in this case we're discussing biochar, is I think a very intriguing opportunity to in my area, which is mostly nutrients, to maintain nutrients in a plant available form, and combinations of nutrient applications, and thinking really in detail about the combination of nutrients and biochar types is a very intriguing approach. And I think also that's an intriguing approach for biochar products that the industry might take on. And I think that leverages industry participation and industry investment in very specific products that they might place for very specific applications.
Yep, thank you. So I fully agree. So the design and the application of the biochar should be driven by the needs in the field, and also driven by the market, so that the tailoring or modification of the biochar will be decided based on the needs and based on the market. So I fully agree with that. So by the way, the other parts of the questions from the other audience is about the feedstock selection. So like you mentioned a lot of the different feedstock, woody, non-woody, or manure, and then how about the potential of like food waste, or maybe some other things that we are thinking at our side as well, like the digestate from food waste or waste co-digestion, those digestate or directly apply food waste. How do you see that the feedstock selection, other than the agricultural residue, the other feedstock, would that be a good candidate as well?
Yeah, I think to consider wastes and wastes is of course a problematic term and usually a transient designation. To think about wastes when they're wastes is a suitable entry point. A lot of wastes that you just mentioned are very moist, and that poses a constraint to conversion because using thermochemical conversion techniques that such as pyrolysis that rely on drying the feedstock, but combinations with liquefaction or hydrothermal carbonization or anaerobic digestion are then really intriguing provide really intriguing thinking models for combinations of such. I would guess that and a suitable hypothesis might be that combinations of approaches will generate larger benefits for harnessing the greatest values out of scarce feedstocks, one might imagine generating methane through anaerobic digestion and then pyrolyzing, and also combining composting with biochar production. But this is really very often a local optimization problem that needs to consider both sides, the front end waste management strategy, as well as the back end, any soil needs or other material needs.
Fully agree. So we need a holistic analysis and optimization regarding the energy balance as well, and also other alternative technologies that we can apply. So maybe let me try to go through the questions. So maybe Yong-Sik, if you see any questions, please feel free. Yes, Bhavani, please.
Yes, I actually have one question from Korea Institute of Construction Technology, which is one of the largest governmental institute, currently working on turning a huge amount of food waste into biochar. And we try to work together, applying them into our land to achieve the carbon neutral. So she sent out a question to me, and thanks for your talk, Johannes. And I'm wondering, you have any advice on how to rationalize energy consumption during the production of biochar, including pyrolysis and any fabrication, in case we have a talk with the policymaker and regulator. So, and that was the first question. And then I guess, Shannon, probably you can ask question directly to Johannes. Thank you.
Yeah, I'm not sure I completely catch the question, but this might be one of those situations where I also always forget to clearly mention that these thermochemical conversion techniques, pyrolysis, these are of course exothermic phenomena. So they generate energy, they don't consume energy. Moisture content is a constraint, and so my rule of thumb that I remember from engineering colleagues is that if moisture content of feedstocks is 70-80% or less, then the material contains more energy than it actually needs to be dried down. So in other words, as long as your moisture content is less than 70%, this is actually not consuming energy, but it's generating energy. And I think that a lot of policymakers actually don't understand that, and that this is, we don't need energy to make biochar. We generate energy to make biochar, and with a caveat of high moisture content. And I agree with you. That is something in a policy talk one probably wants to start with and make very, very clear, because that's also a question that I get all the time. So, but how much energy do you need to make biochar? And I said, I don't need energy. I generate energy, and so that is really something to think about.
Yeah, that's indeed a very important message to get across upfront. So I realized that we have some audience raising their hands. If you have raised your hands, could you please maybe directly unmute yourself and talk and ask your questions directly, please?
Hi, Professor Johannes, this is Xiaonan Wang from National University of Singapore. So thanks for excellent talk. For my research, I have been collaborating with Professor Yong-Sik and Prof. Dan to work on many of the data-driven approaches to model the process and the whole system for the optimization, as you mentioned, between the trade-off of carbon sequestration, the soil enhancement, and the energy production. So we realize a key problem is that the data is always an issue. First of all, the amount of data, and secondly, the quality and how reliable the data could be. So we read a lot of your work, and you as a leader of this whole biochar community have given us so much insight. And we were wondering, as a leader, global leader for this biochar community, do you have any initiative or kind of to cover the data side construction of more global collaborative efforts to build up this kind of biochar data side? I see there are many standards, but I think the data is still following different protocols. Is there any initiative there to build this so that we could better use our nowadays digital tools to analyze even the longer term effect of the biochar, so that to answer many of these unsure questions?
Mm-hmm. That's a great suggestion. Yeah, Shannon, thank you very much for the excellent question. And I'm not aware that there's a central repository for data. And I know that the Edinburgh group is collecting really good data on many aspects. And of course, they're also running a good material reference scheme that then by the same token generates data that come back. But in terms of full life cycle assessments, that there is a central repository, maybe akin to the emerging soil health databases or something like that, I have not seen, or the modeling platforms that are available for doing life cycle assessments with transportation, and so where there are central modeling platforms, or the Phyllis database, or there are these databases that have bits and pieces of the life cycle in it, but one that is specific to biochar systems, I'm not aware of that there's an off-the-shelf established product. So that's a very good suggestion that might either a group or an institution or a consortium might want to take on to generate some kind of platform, and maybe the nascent the initiatives that Edinburgh has started, maybe that's the birth of something like that. But I might also miss some very key players, so excuse me if I missed some obvious examples.
I think you're the best person to lead this initiative, and today the APRU platform could be the platform to host this kind of initiative. If you think it's very important, the whole community could benefit a lot from this, and we could work together to have such data collection initiative. Thank you.
That sounds great. Yeah.
Yeah, there's actually a few other very small initiative is going on, and there are a few of the center like UC Davis Biochar Center, led by Sanjay, is also built up the biochar database. But somehow there's, as you know, limitations. So we probably need to collect all the samples, systematically analyze them again to build up those data set. I guess probably within a year there will be Asia Pacific Biochar Conference, and those suggestions could be a big initiation for the society, at least within this Asia Pacific region, but they can be further extended with a big support from Shannon and Johannes, I guess. So let's further discuss about the issue after this webinar, and thank you very much for the suggestion, Shannon. And
yes,
so
Professor,
due to the time limitation, probably
maybe
Professor Nandi Bolan, you may give a concluding talk, and then we can close. Yes, go ahead. Thank you.
Thank you, Professor Yang-Sik Ok. Thanks, Johan, Professor Johan Lehmann, for a colorful and comprehensive presentation. I just thought I would ask you a question before concluding. I'm attending Australian Organic Recycling Association conference right now, AORA, and I like your last slide, biochar beyond soil, because I was giving a talk last week, the multi-value application of biochar. One of the questions everyone is asking, PAH, polyaromatic hydrocarbon, the contaminants in biochar. Do you think we have the pyrolysis techniques to eliminate or to reduce the PAH, which seems to be one of the major contaminant pollutant in biochar? From your experience, is the feedstock is important or the pyrolysis conditions are important?
Yeah, no, that's a good question, and I agree with you. That is something that's comes maybe right after the energy question we had before, and I mean, with a caveat that I'm not a pH expert, but the experiments that I've been part of, mainly led by Gerard Cornelsen and Sarah Hale from NGI, we've found a wide range of pH concentrations in biochars that we screened. But it was largely predictable that those gasification biochars that had some incomplete gasification, that they could bear very high pH concentrations, whereas slow pyrolysis biochars, none of the ones that we analyzed had any concerns and were mostly much lower than any comparable compost that one would make with the same materials. So I think because we have at least theoretically a good process control on thermochemical conversion techniques, I would say probably better than composting biological processes that are much harder to standardize. The opportunities to make absolutely safe biochar is very very robust in my view. But now, as with anything, if you run a red light with your car and you crash into someone else, you can. That's something we need. There need to be regulations that make this a disincentive to run red lights. So I think, but that should be doable.
Thank you. That's a very positive note. I understand.
Sorry, Nancy, can I ask a quick question before you making your conclusion statement?
I'm sure you can.
Sure, Professor Kacha.
So please go ahead. Yeah.
Hello.
Sorry.
Okay. Yeah. Well, Johannes, thank you for a great presentation. I have a really basic question, and I guess some of the people in the audience might benefit from your insight on this question. I learned quite a bit from working with you on this editorial for biology and fertility of soils. And so the question is, can you help us out in defining the historical perspective as to what exactly is biochar? If we convert a feedstock into a biochar and we use that as a fuel in the future, would that still consider to be a biochar? And I guess from my understanding, you would define biochar as initially being used for soil application, but if it's being used in your last slide, if it's being used as a food ingredient, would that still be considered biochar? Something like this.
Yeah, no, thank you. Good to see you, Scott. That's a good question, and of course, this is something that we all determine. Individuals can make suggestions, and then history proves them wrong. So because I have my own blinders, I know at some point I was part of a community that defined biochar as a soil amendment, and then other people are using that same material and making walls and teacups and all kinds of or streets out of it, or hamburger buns, and so this. I think this is just happening, and I would agree that we probably want to call biochar with an expanded definition, not just as a soil amendment. It's a material property definition, but also a definition for possibly environmental remediation, but also possibly just around a climate change mitigation. But this is really something that is developing, and so it's I think it's up to all of us to work on that definition and put it all in a pot, and then we'll stir it around, and hopefully we come to we might never come to a complete agreement, all of us, but at least we have maybe something that develops over time, and it's good if it develops and changes. So I think that's speaks to a lot of brilliant minds and a lot of interests that circle around it. So that's, I think, a really good sign.
So so thank you, Scott, for asking such a big question, and very happy to see you. Scott was my former postdoc supervisor, actually. So I guess there are still so many questions comes up, but we're supposed to finish at 10, but it's already 10:30. So I think this is one of the long-lasting webinar that since we started this webinar series. So I would just suggest whether it's technically possible for ask people to join and take a group photo together with Johannes and or because there was some suggestions. So we'd like to take a photo all together just for memory.
Okay, so then maybe a few minutes. So I will add.
Not for a few minutes. Maybe you can try in 30 seconds, and we have to finish it within 2 minutes.
Okay.
Not all, but you can bring just some people, and just 20 people should be okay.
Okay.
Yeah. And anyone who joined this, please turn on your camera and please join taking a group photo. If you cannot, you can log out. Okay.
Yonsek, while Kumu is working on this, Nancy, sorry I took your time away. So it's your time to make the concluding statement.
No, it's okay. There's no conclusion. Actually, I guess Johannes already made a big conclusion for the definition of the biochar. So I think that's really good end of this presentation. And I'm doing a lot of other applications, so that give another pretty good job opportunity in other application field. So.
Okay, Nancy, sorry, Yonsik is the boss.
So, Professor Wong-Sik, do you want to make any concluding statement, or it should be okay?
No, it's okay. It's okay.
Okay. Thank you.
Okay. Okay, so look like we have enough people. So, Kumu?
Yeah, keep smiling like Dan.
You may say 3, 2, 1 or something, and how we can take a photo that you can try capturing, and we can share with all.
Okay. Can you all turn on your camera?
Yes, we did.
Okay. So I will take a picture.
Yeah.
1, 2, 3. Okay. Thank you.
Okay. So again, Johannes, thank you so much for joining this webinar. It was really enjoyable, and thank you, Shannon, Scott, Dan, and Professor Nandi Bolan, and all the friends, and Hairong. Thank you so much, and you have a wonderful time, and let's keep work on this biochar. Okay. Thank you. Bye-bye.
Thank you.
Thank you.
Bye-bye.